Welcome back to video 2 of the Introduction to Thermodynamics by the International Consortium of Advanced Technologies and Security. So here we need to ask ourselves, how do the laws of thermodynamics relate to thermal imaging, to the field of thermography? Why do we need to understand them? We need to understand them in order to fully grasp what is happening in the various types of devices or uses we put forward in the field. How the heat is generated, how it gets to us. In the image you're looking at, we have a power supply and a sensitive piece of radio equipment, which, since it both sends and receives a signal, the power supply itself can interfere with those signals, the interpretation of them, in the various forms that radio waves are used, just by having an issue with the rear contact. In this case, the issue would be the power, could be power supply failure if it's allowed to go to failure, and then of course that would cause equipment failure because the power is gone. This is in an air-conditioned space, and so nothing seems hot as you walk past. You don't feel the radiation coming off of this device, but the infrared, the thermal imaging device can see it. However, we can spot this problem, and this problem was immediately repaired because of the high priority and importance of this piece of equipment. In this space, there were a number of these that were corrected immediately. But what is the issue? Your clue to answering this is that the fan motor to the upper left in the image is generating heat. That's why it looks hot to you, because it is pushing air. So it's doing work. Second law of thermodynamics, a little bit of energy or heat is always lost in every energy transaction, and here you have, in essence, an air pump or a fan that is moving air, and air is a fluid, it has weight, therefore it's putting out energy, it's burning watts, joules are being expended, turned into, expressed as energy of air being moved, and so you have heat being generated, and this is normal. The real issue here is the hot contactor, where the red arrow is pointing. Practice in the field with your level 3 instructor will show you how to tell the difference by attenuating the image that you're looking at. Here are 3 images of the same motor. Left to right, this is what we call a real-time or an actual visual image using visual light range. The infrared thermograph that is used in the report, and then a picture-in-picture image of the same device. And the picture-in-picture allows you to see in context what the problem is and exactly where the issue is. It focuses your attention, much like the red arrows would for the technician that goes back to repair these. So thermodynamics is taken from 2 Greek words, therme or heat, and dynamis, where we get dynamite or dynamo, meaning to move, dynamite, strong, powerful, strength. Okay, lots of uses for that. In English we have a much larger vocabulary and than any other language actually in the world, twice what the next one is, and that's German, which this is based on. But so dynamis, dynamo, we use it to indicate strength or power. So those thermodynamics is it's kind of easy to remember, is the movement of heat. It's accurately remembered that way also, but it is the branch of physics dealing with energy transformations from and into thermal energy. Engines use fuel for energy and so must make and then lose heat. But they will all have rules that tell you if this is normal or abnormal. You know, a diesel engine is going to have heat, and then you're going to have heat as it removes it, and through its various ways of venting that heat out. If the heat's somewhere else, or if one of the cylinders is not hot, then you have a different kind of problem. You have to analyze each of those issues. In mechanical systems, they are governed by Newton's laws. Heat is usually indicative of a problem because the internal energy of the system and its ability to work well and efficiently depend on how low the friction is, how low the resistance to movement is. In electrical system or electromechanical systems, say the motor, like you can see here, the motor heat can be a normal byproduct or an abnormal byproduct that is a problem. If you block, physically hold your hand up and block the bottom part of the thermal image there, you can kind of get a grasp, or at least mentally block that. You can get a grasp of what the motor should look like under normal conditions. The only thing abnormal here is the front of that motor. We'll deal with this particular one later because it's important to understanding lubrication and why ISO standards are what they are and how they're made and created to prevent the lubrication failure, which would cause bearing failure, which would cause motor failure, which would cause the device it's driving to stop working. In the electrical system, which you'll see pictures of in a minute, the heat is almost always a problem. The exceptions are transformers, resistors, relays, coils, and lights, light bulbs, incandescent especially, which all give off heat of their own, and they are supposed to. A light, of course, gets the energy excited enough to be able to be given off as a visible light that's quite warm as far as thermodynamics is concerned. But transformers, resistors, relays, and coils always have heat, and if you're looking at, let's say, a motor controller, you're going to have some relays, resistors inside that, and heat is normal in those cases. In thermodynamics, we think about quantities which describe the system we're looking at. Volume, temperature, the pressure of gas, tell us about the system and the work it can do, etc. Electromechanical systems do work and therefore have waste heat, which is not necessarily an issue, except it might be an environmental issue, that is, how hot the area is, or the efficiency of the machine itself. It could be wasted heat, wasted energy that gets into the environment that needs to be removed, or it might be an inefficiency that the machine is experiencing. But in thermal imaging, we're dealing with what is hot, why it is hot, where the energy is coming from, and how did it get into our imaging device. So it's necessary to differentiate between heat that is normal and heat as an indicator of a problem. And so this is a qualitative issue as well. Thermal energy is that particular energy given off as electromagnetic radiation. Until that is emitted as radiation, that same energy was kinetic energy, literally molecular vibration. Friction is a good example of this. If you rub your hands together real briskly, they'll warm up. We do that on cold days and such. Boyle's law, in a fixed amount of gas at a fixed temperature, pressure, and volume are inversely proportional. In most bodies of mass, that energy is given off as infrared radiation. Here's a principle. Short wavelengths of light, say UV light, ultraviolet, has more energy than long wavelengths of light, say infrared. The application is, turn on an incandescent light bulb under low power. This is kind of a proof of that. At first it becomes hot, giving off infrared light, and a thermographer can see that even though you might not be able to see any visible light. It's being given off as infrared. Turn that power up and those red wavelengths shorten into the visible red range. It glows red and you can see it. Turn the energy up a little bit more and the light given off turns towards yellow. This is warm yellow light, in other words, or warm white light. Some warm white incandescent bulbs, if you can find them anymore, are in this range. They're a yellow, a white light shifted towards the yellow. Add even more energy, and the light given off has shorter wavelength. It has moved into the cool white or into the blue range as the filament becomes hotter and the wavelengths get shorter. Let's review the 4 laws of thermodynamics. The 0th law of thermodynamics states that between bodies of different temperature, heat will always flow from the body of higher temperature to the body of lower temperature until the temperature of the two bodies are the same, or they are in thermal equilibrium. The corollary to this law is that if two systems are in thermal equilibrium with a third system, then they must be in thermal equilibrium with each other. So this is the first law of logic. A equals A. Of course, it applies to everything. So if block number 1 is in thermal equilibrium with block number 2, and if block number 2 is in equilibrium with block number 3, then it's necessarily true that block number 1 is in thermal equilibrium with block number 3. At thermal equilibrium, there is no energy left to do work between those bodies, and so zero work is being done between them. Zero energy is being transferred. The first law of thermodynamics can be stated thusly: energy in a closed system is a constant. It is not being created or destroyed. Rudolf Clausius in 1850 stated it this way: in a thermodynamic process, the increment in the internal energy of a system is equal to the difference between the increment of the heat accumulated by the system and the increment of work done by it. For all adiabatic processes, that is, where no heat is being exchanged, between two specific states of a closed system, the net work done is the same regardless of the nature of the closed system and or the details of the process itself. The second law of thermodynamics states that the entropy, or the disorganized energy in a system, the entropy of an isolated system which is not in thermal equilibrium, always increases. Many ways of stating both of these laws, all of these laws. One is energy always flows down a thermodynamic gradient. That's my favorite aspect, actually. Isolated systems spontaneously move towards thermal equilibrium, the state of maximum entropy of the system in a process known as thermalization, and so heat is flowing from the higher energy system to the lower energy system, trying to reach equilibrium. Heat and work are forms of energy transfer. That was Joules's law also. So, the third law of thermodynamics states that the entropy of a system approaches a constant value as the temperature approaches zero. In other words, the entropy, again, if it's flowing down a thermodynamic gradient and the gradient is getting smaller, then the entropy, or the change in the available energy for work, is dropping. But as it approaches zero, and that's 0 Kelvin, so that's absolutely having no energy at all. The entropy of a system at absolute zero is typically necessarily zero. In all cases, it is determined only by the number of different ground states it has. A little bit hard to measure it without that idea. Theoretically, no one has actually been able to get anything to 0 Kelvin, nor find anything that is 0 Kelvin. But in theory, when they're trying to calculate how much energy has come out of the system, how much is left, they claim to have come very close to 0 Kelvin. It's a little bit hard to measure. You can't. There's no metric that you can do. It has to be a calculation, and this is one of the reasons. Specifically, the entropy of a pure crystalline substance at absolute temperature is zero. Again, this is theory. It's never been proved. It's never been measured. It's very hard to get something to that energy state of 0 Kelvin. Conduction is how energy travels through a physical mass, and it does so using thermal motion. Thermal motion is disorganized random motion of constituent atoms in molecules with any body of matter. It also flows from higher energy to lower energy, from organized to disorganized, always down a thermodynamic gradient. You can see the ICATS 2006 evaporation condensation presentation to understand emissivity, which is a key component in understanding the thermal energy. It has to be emitted. It has to be transferred to the surface and then emitted as thermal energy or thermal radiation in order for us to see it. Well, that brings us to thermal energy, which is the kinetic energy of thermal motion, the translational, rotational, vibrational energy that's associated with a mass. With a thermal imaging device, we see that thermal energy as heat. Heat is the thermal energy transferred from a region of high temperature to a region of lower temperature. Mass stores thermal energy, or internal energy, and so heat equals the thermal energy in transit. Heat is easiest to detect using a thermal imaging device. Temperature is the measure of average value of the thermal energy of atoms and molecules, not the total amount of energy, thermal energy in a system. Look at the distribution curve below here. What most people don't realize is, let's say you have a glass of water that is 70 degrees Fahrenheit. Okay, what does that mean? That really means you're measuring the average of all the molecules that are in there and their motion, their ability to cause the thermometer, which is touching them, to vibrate in such a manner that the liquid inside of it, be it a metal liquid or other kind of liquid, that is mercury or other kind of liquid, expands, and then you can take a reading off of that. It's a measurement of that movement. The movement in those molecules is spread across a distribution curve. To the left on the curve that you're looking at the bottom here, that distribution curve says some of those molecules are probably near freezing, that is, near the point where they form ice. Okay, that's not absolute zero, that's not 0 Kelvin, but close to the temperature where they're moving ice. Now, some of that is also at the other extreme. It's got enough energy to become a gas, to leave the surface and to evaporate. If you don't believe that, put a glass of water on the table. In fact, put salt water on the table, so then you can see not only that it evaporates, but that somebody didn't pour it out while you weren't looking to get rid of the water. You'll find the salt left in there as evidence of the fact that that water evaporated. So some of that energy is at the high range, some is at the low range. Temperature is a measurement of the average value of the thermal energy of the atoms and molecules. Okay. It's a measure of the ability of randomly moving particles to impart that thermal energy to a thermometer, specifically to the fluid that's used in that thermometer to indicate the temperature. And the temperature in Celsius, that is the centigrade range, or in the Fahrenheit range, Kelvin, whichever you want to use. Well, which do you want to use? We will always use the Celsius or centigrade range. That's the international standard. We'll be working around the world. It's very helpful to know that you're communicating something meaningful to somebody else. But how did these ranges get? How are they developed? Well, the Fahrenheit scale, which we usually use in the United States, was Gabriel Daniel Fahrenheit. And he created a reproducible thermometer which used mercury, so it didn't wick up the sides of the glass, because it would normally wick and it's hard to read. Do I read this upper portion or the lower portion? Where do I take that measurement? Well, mercury doesn't do this, and so it gives you a good level to read. So he invented that in glass around 1750 AD. He set the 0 point at the lowest temperature of the winter of 1709. He is said to have used his wife's body, this is unknown if it's actually true or if it's an urban legend, but his wife's body heat to set the set the 100 degree point. But this resulted in a freezing and boiling point that were at partial degrees. So he stretched that range, and body heat became, so boiling became 212, so it was a full range, and her body heat suddenly dropped to 96.8 degrees. And then freezing was moved to 32 degrees, so both of them were whole degrees. So there's 180 degrees difference between freezing and boiling. So it's not a centigrade, that is, it's not a 100 gradient distance between the two, it's 180 degrees. That'll be important in a minute when we multiply one times the other by 1.8 in order to translate it from one to another. Okay. Celsius scale. Celsius was a Swedish astronomer, and he set 0 as the point where water froze, and he measured that many times to make sure that that was the right one. That was ice. Ice was formed in pure water at 1 atmosphere of pressure. So 100 became the boiling point of water. So that is a centigrade, right? It's 100 centa, 100 gradients between the freezing point or melting point and the boiling point of water. Boiling point is where, of course, it starts more energetically to go into a gas form or evaporate. Also, that's where it starts to condense more, and the colder it is, the more it will condense, of course. You lose the energy. Remember, this is vibrational energy. So as it vibrates, it gets farther apart. It goes from an ice where it's a solid, it translates to another form of matter that's a liquid, and then at some point it goes into a gas, and that's at 100 degrees. That happens more energetically. 100 degrees Celsius, 212 degrees Fahrenheit. Okay, so the relationship between Fahrenheit and Celsius in degrees can be expressed by these formulae down here, the various formulae. There's only one that you need of that, and I would encourage you to memorize, and that is the one in red, of course, that the temperature in Celsius is equal to 1.8 times the degrees in Fahrenheit minus 32 degrees. The reason I say that is there's only two here. They're expressed differently. Okay, the top and the bottom are just different, or rather the left and right in each top and bottom are only different expressions of the same one. And so if you memorize one, you can figure out the other one if you're in the field. So it's helpful to understand a little about the scales and why they were developed and how the gradation went, and why Celsius is called used to be called the centigrade scale. Take a little bit of a mental break here, because you don't really need to know Kelvin too much, but you do need to know what it is and what it means and how it became there. In thermodynamics proper, they will use the Kelvin scale. Lord Kelvin was one of the earliest scientists to consider the issues in thermodynamics, really one of about 6 to 8 men that really added huge amounts to the understanding of heat and how it was given. His actual name was William Thomson, without a P. He was a Scot living in Belfast, what we in America would call Scotch-Irish. They're actually Scots that were living in Belfast, moved there for political reasons by the king, and we're still having issues with that today. But he debated with Joule about the nature of thermal energy itself and the caloric theory, where heat was considered to be a type of invisible fluid called the caloric. We still have calories as a unit of heat, but the caloric theory itself was different from that. It's no longer believed by anyone. But he Lord Kelvin that is, detailed several theories of thermodynamics and was the first science to enter the House of Lords. Okay, this is where he derives his title, Lord Kelvin, from his schooling at Glasgow University, where the river Kelvin blends into the river Clyde. Well, he was given the title of the first Baron Kelvin. So that's why we name him Lord Kelvin. To the left here, you can see some different temperatures in the Kelvin scale and kind of understand where he was headed and how it's used. Now, it is a centigrade scale. It is based on Celsius work, but it starts at absolute zero. So 0 Kelvin is no energy whatsoever. Nothing has ever been found to have 0 degrees Kelvin, and in my cosmology, if correct, that is the point at which a solid object would cease to exist in our physical form and turn into what is really just now being at least rediscovered. Used to be called ether, now it's called dark matter and dark energy. That's probably the point where those that translate one into the other. Now, keep that secret. No one knows it yet. It'll take them 30 or 40 years to figure that out. But to give you an idea, helium itself boils at 4 degrees Kelvin, or minus 269 degrees Celsius. It's really cold. We used to use a liquid nitrogen to cool off a dewar in the old and very large thermal imaging devices, and liquid nitrogen boils at 77 degrees Kelvin. Very, very cold material. Glad we don't have to haul that around anymore. Another unit of energy is a joule. It is heat from energy. We can always use a joule to describe that energy as work. More common in thermodynamics is the calorie. Remember, not the caloric theory, but the measurement of a calorie. By definition, 1 calorie is the amount of heat required to change temperature of 1 gram of water by 1 degree Celsius. Now look on your screen, realize that a gram of water is about that which would fill that 0 degrees by the Celsius, that degree indicator. If you put it in there, it would just about fill that on a flat screen. It's a very small amount of water. So 1 gram is the weight at 1 atmosphere of 1 cubic millimeter of water. Now in food, we use kilocalories, or a large C. So 1 food calorie, a calorie of food, is actually 1,000 calories, or a kilocalorie. Now, Joule argued in 1845 that the mechanical power exerted to turn a magnetoelectric device is converted into the heat evolved by the passage of the currents of the induction through its coils, and on the other hand, that is the motive power of the electromagnetic machine is obtained at the expense of the heat due to the chemical reactions of the battery by which it is worked. In other words, he recognized the energy of the battery was being turned into work energy by the coils. Some of that was heat, some of that was work. So he is therefore credited with the first law of thermodynamics, discovering it and describing it. Okay. Both the first and second law are found in his Christian defense of the Creator being the only being that could create or destroy energy. So his worldview of God, the God of the Bible being the Creator, caused him to look at the scientific evidence in a specific way. And when he was told that the energy from a fire is higher than there's more energy in the fire, it's more energetic than the water it heats, the claim was that that energy was being destroyed, and Joule stated it this way: there is an enormous loss of vis vita, or work energy, in the passage of the heat from the furnace to the boiler. Believing that the power to destroy belongs to the Creator alone, I affirm that any theory which carried out demands the annihilation of force is necessarily erroneous. In other words, they'd come to the wrong conclusion because only the Creator himself could create energy or destroy it. So that's the first law. Energy is not now being created or destroyed. That's also the second law. What happened to that energy? It's directly implied here. The energy was just lost, or entropy increased. So he restated the first law and directly implies the second law, claiming the energy had to have been lost to the system, or it's become less organized, or entropy increased. That's the second law. Right guy. Okay, in units of heat again, we turn to William Thomson, Lord Kelvin, and to Joule, and the British thermal unit in this case. The English unit of heat is called the British thermal unit. It is the amount of heat required to change the temperature of 1 pound of water 1 degree Fahrenheit. Now this is a UK, well, not a UK pound, but it's a UK gallon of water, so it's 1/10. So a UK gallon is exactly 10 pounds of water. It's only 0.1198 US gallons, which weighs, a US gallon weighs 8.33 pounds, at least pure water does. If you add salt to that, salt water becomes a little bit heavier. Okay, so conversions. 1 BTU is 1,055 and a little bit of change. It's 1,055.05522, I think, joules. 1 calorie is a little bit over 4 joules. Again, I think it's 4.02 something, 023, I think. And a BTU then is 252 calories, or 0.25 kilocalories, again with a large C. Okay, let's look at temperature versus heat. Everyone has a qualitative understanding of temperature. It's the quantitative aspect that gets us. So we feel differently at different temperatures. But nerves best inform us of the differences, but it is not exact. Okay, I reached into a 400-degree oven yesterday, 400 Fahrenheit, of course, and it was not overly hot until my finger slipped off the insulating a pad that I was using, and I touched the 400-degree Fahrenheit Pyrex dish on the side. Why did my finger suddenly feel a lot hotter enough to make me move my finger? Well, the air and the rack are the same temperature, but they have a very different energy constituents and the ability to transfer heat. There was conduction going on, and that's why you put things in the oven, because there is conduction. It heats it up. There's radiation going on. I could feel that energy coming in from the side, and that was directional. In this case, hands towards the center, the back of the hands were hotter than the front of the hands, which of course had heat pads on them. But I became a very highly efficient thermal conductor when I touched that Pyrex dish. And it didn't burn myself. You move yourself away fairly quickly when you feel that. But that's heat versus temperature, and the transfer of heat, or radiation and convection, versus conduction. When you touch something, you become the conductor, and it's true with the electricity also, so be careful. But you become the conductor, and humans are very good conductors of heat. They're also very good emitters and very good radiation absorbers as well. To understand the laws of thermodynamics, it's helpful to understand the internal energy of a system and how it's changed. So let's review those laws one more time. The zeroth law is that energy always seeks equilibrium. The first law, per joule, energy is not now being created or destroyed, or the total energy in a system is constant. The second law, energy always flows down a thermodynamic gradient. In other words, entropy always increases, or it always moves from the hotter to the colder. There's lots of ways of seeing that. Work done by the system. There's some loss in every energy transaction. There's some energy lost in the transaction itself. If you remember, some time ago we looked at a power supply and the fan. The fan was just, its job is to move air through that system and extract the heat out of the system via the air. So in that case, it was radiated heat from the system itself, heating up the air, so that's Carnot, and then extracting that, moving it out of the way as you move that fluid we call air, atmospheric air, out of that device. But there's some heat loss, so it looked hot. It's all the second law of thermodynamics. It's flowing down a thermodynamic gradient. The third law is that at 0 degrees Kelvin, entropy is also 0 Kelvin, or the entropy of a system approaches a constant value of 0, actually, as the temperature approaches 0. So there's less and less entropy as you approach 0. The colder it gets, the less work can be done, right? Heat is energy that moves into or out of a system because of a temperature difference between the systems and their surroundings. Work, on the other hand, is the energy exchange that results when the force F moves through an object at a distance d. So work equals F. Equals F times d, or force times distance. Again, the subject is, how does thermodynamics apply to heat transfer, in our case, into thermal imaging or thermography? Okay, well, there are three methods of heat transfer. That is conduction. We just talked about that a minute ago with my finger touching the Pyrex dish. The transfer of heat between two parts of a stationary system caused by a temperature difference between the parts. Transmission is through a conductor. So my finger became the conductor. So the vibrating energy of the particles, some was being given off as infrared light. It was convecting, conducting, but my finger became part of that and conducted that heat. Thermal conductivity is the ability of a substance to transmit heat to another physical part or another physical object. It depends on the atomic or molecular structure and the physical state the mass is in at the time. Quite literally, it is the passing of heat by molecular collision with adjacent molecules. Your nerves sense those collisions. Things are speeding up inside. Your finger says, this is hot. Your neurological response is, move your finger. Okay. The second method of heat transfer is convection. Again, back to the oven. That's why you put things into an oven. It creates that heat. Carnot says it's radiating out and heating other things, and also it convects. It moves air around in that oven. Now, a convection oven is a little bit different in that it actually moves the air, and that helps to transmit that heat even faster. by moving the air itself around inside the oven. Okay, convection is the transfer of heat by circulation or movement of the heated parts of a liquid or a gas, that is fluids. The change in the density causes molecules that are warmed in the fluid to rise up and the cooler molecules to drop down. Again, the molecules bump into each other, speeding up one and slowing down the other as the heat is transferred. When it's transferred to a physical mass, like let's say the Pyrex dish or the food that was in it, it translates back into molecular motion, where those molecules are bumping into each other. Okay. Radiation is the opposite process. That is, it's when heat conducts out to the surface, some of that energy, it is emitted as infrared particles or other particles. Hopefully what you're seeing is not above the infrared, or that is below the wavelength of infrared. It would mean it was a lot hotter. We have seen those, though. There are stories we can tell you about ships and other objects that have been glowing red. They were so hot. In other words, the wavelength shortened into the red range, and we could see it with our eyes. But radiation is the process wherein energy is emitted as particles, light energy. Thermal energy is transferred through a medium to a different object by absorption of electromagnetic radiation, such as the Earth receives 1.4 kilowatts of energy per meter by radiation from the sun. So the radiation, the percentage of energy emitted is called emissivity. It's the process of emitting. It is expressed as it's a dimensionless number. That is, there's not a dimension. It's not time or not time or distance, but it's a ratio, and it's usually expressed as a decimal. Up to 1, of course. 1 would be 100%. If it was over 1, you'd be you'd have cold fusion. You'd have something that doesn't actually happen. You'd have more energy being emitted than contained. The box pictured here is an evaporation condensation desalination unit at San Diego State University, where I was an adjunct faculty member. This is one of my projects. I was the principal investigator of this project and others. This device is radiating energy, which is apparent to us all. You can see it in the thermogram, but it is also convecting inside, which is so it's making clean water from the salt water. That is, its evaporation condensation is distillation, so it's making distilled water. The salt water is entering in the unit and coming out as very pure water. But let's treat this image for a second as if it were a solid block, which is conducting energy through it, then to the surface. Note the arrows are coming through the image itself. The mass, A, is passing heat through it, which is the blue arrows indicating, and this conduction of heat through the mass. And only then the energy is striking the surface and being emitted from that surface as radiation. The conduction itself can be described as the rate of heat flow through that mass. Since this is a rate, it is divided by time, and since time is a dimension, it's not a dimensionless number, so we have the Q over T, which equals time, okay? That rate is the thermal conductivity of the mass multiplied by the contact area if we were conducting from one mass to another, as it is frequently the case, and actually is here, since this is a box made out of 316L stainless steel, and you can see the hot edge, let's say right in the center or at the top and on the left. Those are edges or corners. There's other ones here, but those are edges or corners you can see, and where actual conduction is taking place. Okay, and so it is that you multiply that by the difference in the temperature in Celsius and divide by the thickness of the mass itself to understand the conductivity of this. And you can get fairly complex in thermography, but it's not always necessary. But when you're presented with a complex picture, you need to understand where that energy is coming from, how it conducts, how it convects, and how it radiates and from one into another. Let me show you what I mean. Here is a short list that you're going to need to understand before we get to that complex picture I was talking about of conductivities of various materials. Not listed is bakelite, which is what we're going to be looking at, which is a plastic used for more than a century now. It was first marketed in 1907. I think it was the first plastic that, the first polymer that used formaldehyde as the solvent. But it has a slightly lower conductivity. That is, bakelite has a lower conductivity than the Teflon shown here. Teflon is a polytetrafluoroethylene. Bakelite is a thermoresistor, and its conductivity is 0.21. Very low conductivity. Look here also, you'll see copper, which is inside the box you're going to look at. Copper has a conductivity of 401 watts per meter. So that's a very high conductivity, as does gold or silver, even higher at 429. So they're good conductors. Wood is, of course, a very poor conductor at the bottom of the list at 0.13. So you need to know a little bit about conductivity of materials that you're looking at. Emissivity is a dimensionless number. It's a ratio, but we express it as a decimal, so it becomes dimensionless. It is the coefficient expressed as a decimal of the amount of energy that conducts to the surface of a mass and that emits or radiates from its surface. You need to understand this. This is a very brief listing of some of the various emissivities of a few things you'll run into. Notice here the polished copper, and then what happens to it when it is heated and it oxidizes. A very critical issue to a thermographer, an issue that you're going to deal with when you're actually writing a report. Why do you need to cool off this copper contactor? Because it's going to oxidize, and when it oxidizes, it's going to lose more of its heat, but it's also going to generate more of heat. You become a high resistant joint. Okay, so the emissivity changes over temperature range and with oxidation, but the number rises in the copper from about 5% or 0.05 to 0.78 or 78% of the emissivity. Many conductor devices you will see are made of these metals, and herein lies the issue. When the temperature rises again, they oxidize. They emit more of their energy, but this indicates the heat is building in the device and it's moving towards criticality. It'll catch fire, the insulation could catch fire, or it could actually explode if it got hot enough. In the complicated device that we're going to see next, you need to understand this also. Now we're to the complex issue we were discussing. This is a breaker box. It's a complex picture. Why? Because you have a lot going on here. So what is the hottest point is the question. Where is the actual problem? Well, it turns out to be the internal contacts are the hottest point, but the hottest apparent point is the external contact. You could actually see at the lower left if this were a visible light image, if it were what we call a real-time image. Okay, but think about how the heat comes to your imaging device to make the image that you're looking at. Okay, it's apparent heat, right? So how did it get there, and how is that complicated? In this case, it is made by a high resistance internal contacts inside the device and wicking out to the contact that you see at the outside of the device to the left. But from there it radiates. But from there on the internal contact, that is, both of them are radiating to your device. One is radiating directly through the external contact that you can see, but the other one radiates where the contacts are the hottest point, radiates into the void that's around it. There's a little bit of air in there, right? The air convects, becomes hot, eventually becomes stable, and that further oxidizes those contacts, making even more of a problem. But some of that convects into the bakelite that is the box itself. It's a black or gray or brown box, and then poorly through that bakelite. Remember, the conductivity was very low. It was 0.21 through that bakelite and out to the imaging device. So as a thermographer, you're seeing only a fraction of the heat that is actually inside the box. Remember, the zeroth law saves us here as thermographers, but destroys the contact slowly, because the hot contacts seek to equalize within the small air void to both the bakelite on the outside, but it's draining out through there. It's seeking to equalize it also to the contacts, which are actually giving off the heat, but some of that heat goes back to that contact. It's convecting, right? So the heat is in both directions. The air void with the contacts and the bakelite, it's trying to seek that equilibrium. So that's the zeroth law. And eventually all the heat dissipates, but more electric energy is coming in, the resistance gets higher, the heat increases, so you have a heat flow out to the thermal imaging device every second that this device is on. Only when it's off does it reduce down to ambient temperature, right? So this apparent 26-degree rise that you can see on the right side of that image but it's on the thermal contacts will become a 50-degree rise in a year, and then become critical about 6 months after that, somewhere in that range, according to how it's used. However, the internal contact is already probably 100 degrees C above the ambient. It's critical right now. It could fail now. It could blow up or start a fire. Most likely it'll keep tripping this device, and they won't know why the device is tripping. Well, the device is failing, and that's better than causing your system to fail in some other way. That's what the breaker is there for. This breaker box needs to be replaced, and it needs to be replaced now. In this case, it's tripping constantly. That's better than the other alternatives. But this is how understanding the law of thermodynamics, the laws of thermodynamics, helps you as a thermographer. Without them, you understand what the apparent temperature tells you through the image, but that could be what would be classed as serious now is classed as an immediate problem that needs to be fixed. It's a critical problem in reality. So that's the ISO standard. So let's take a look at those to understand that. The text that you see here is actually an image, even to me, put into the PowerPoint. It was actually copied directly out of ISO standard 18434-1, the International Standard for Thermal Imaging Problem Categorization. It is easy to work with, where the lowest priority is every problem below 10 degrees centigrade, and is classed as an advisory. In other words, tell the client about the issue. You've got an issue here, just be aware of it, or track it, put it in your preventative maintenance program, or next time you are doing maintenance, tighten this up, whatever your advice to them might be. But from 10 up to 20 Celsius, or twice the temperature rise, the issue is classed as intermediate. This is becoming more of a problem. And remember, this is going to, the time will be reduced moving from one to another, even though it doubles, and then it doubles again. So from 20 to 40, again, double the previous rise, this issue would be classed as a serious issue to be dealt with. Above 40 degrees centigrade, rise from the ambient temperature, that is, it's classed as a critical problem. So the problem pictured here, again, what first looks like a 26-degree rise is a serious problem. It's really a critical problem according to this standard. Serious can be a common term, it can be ambiguous a bit, but critical. This is a critical issue that needs to be dealt with quickly. Well, as we have seen, thermodynamics relates to virtually everything. As we saw in the first module, there are fundamental laws of science. They are fundamental laws of science, and all other scientific laws are derived from them in one way or another. They are applicable to all machines and animals, from medical issues to machinery, mechanical issues to electrical issues, from equipment failures to fires and explosion. It's all about the energy in the system and how efficiently that system is operating at the energy level that it's required to operate at, or that it does operate at. And thermodynamics can give us a lot of information about those systems and how they operate and how they are operating.